And C-quarks are actually they drive some of the key properties of the proton. They determine some of the key properties of the proton, and by doing this quantum tomography, we would actually advance our knowledge of it and try to see what is the origin of those properties. But that is difficult. So what we do instead is to try to measure projections of this model distribution, which is a Wigner function. And what we do instead is to measure projections of this quantum density. And there are various ways in which you can project the complete quantum density in terms of rather momentum dependent position or momentum space. And there are different ways that you can connect one another. This is a nice diagram that I took from some paper. I forgot to include the reference here. But this is the idea. You don't go directly with the Wigner measurement, but rather try to get the pieces of it and reconstruct the entire picture out of that. So in doing that, we not only aim to actually measure those functions, but also to explore aspects of the quantum chromodynamics, the theory of quantum chromodynamics, which are not very much explored. What I mean by that is the 3D structure of the protein and how, what are the evolution equations that govern those functions. So we would like to see the protein in 3 dimensions, but perhaps more importantly, to study the underlying theory and how is it that the underlying theory looks like in 3D and when you change the scale as well. So we actually know the one-dimensional solution since 1977. So this is a work by Guido Altarilli and Giorgio Parisi that we all know. But aspects of the 3D equivalent of these equations actually escape us today. They're much more complex and therefore more interesting than the one-dimensional version that Guido and Giorgio discovered a while ago. And so you can see from here, this is a very, I just checked today, this is a very influential paper that is just going strong. And when you see here the plot of citations per year, but even there, this is not Parisi's most famous work. As you may have noticed today, he received the Nobel Prize for a completely unrelated work. So interesting fact. So the quantum tomography of the proton requires a new tool that has high luminosity and high beam polarization. We would like to explore what is the 3-dimensional structure of the proton when you vary the spin. If you are able to control the spin of the proton in both the longitudinal and transverse direction, we want to see how is it that the structure changes and how that structure manifests itself in observables that we can measure. So the EAC is the perfect tool to study that. And moreover, the EAC will be a jet factory, just like any other collider in history, since the first Hadron Collider at CERN, the ISR. But what will make the EAC unique and distinct is that the jets that it will be produced at the EAC will be the first ones that are produced in proton polarized deep inelastic scattering and in nuclear deep inelastic scattering, which were 2 reactions that HERA did not have the capability to provide. And here I'm showing you just a few event displays of the different types of reactions that we will be able to study in the EAC. Many of them involve jets and the final state, and they're rather different reactions like deep inelastic scattering, but also diffractive scattering and photoproduction, even charged current, deep inelastic scattering, and so on. And so the topic of jets itself at the EAC is very broad, so I will concentrate on perhaps what is the simplest one reaction, which is the neutral current deep inelastic scattering, where you observe a single jet in the final state. So this is represented on the left by the Born level diagram, Feynman diagram, where we all know the electron scatters is out of a quark, a single quark, and it reduces to the lowest order a single jet. And so that is what we would expect, and this is what we actually see. If you see on the right-hand side, experimentally observed in the HERA collider. So one of the key aspects of this reaction is that it is actually rather clean. And you can easily identify both the electron, the scattered electron, and the jet kinematics. Out of that, you can actually reconstruct what were kinematic variables that are involved in this reaction without all the soft interaction and underlying event that is present in other hadron colliders. So interestingly enough, this channel that I'm showing you here, the single jet channel and deep inelastic scattering, even though it's the most abundant type of events that we will produce at the EAC and the ones that were produced at HERA, was for a long time considered a background. So this was considered trivial, not interesting. It's like it was called the quark particle model, and even more than that, it was considered, or it was called the naive quark particle model. Okay, so it was not naive when you considered a high-angle gluon radiation that produced more than one jet, and that was only what was considered in most of the papers of HERA. That was considered actually the interesting part. This was like mostly a background, but that actually changed recently, very recently, with I would say papers that will become classics in my humble opinion, which introduced the concept that you can actually use this reaction to constrain the transfer momentum dependent PDF with the quark PDF, and their evolution. So this was work by Liu et al. And independently Gutierrez et al. The two different methods, different papers actually are different. They use different assumptions and arrive at different factorization formulas and so on. But the principle is that in both cases, you would want to use this channel actually to constrain the quark TMDs. And the key advantage, and this is a quote from one of the papers, is that when you do this by measuring jets, you actually don't involve in the theory calculation the fragmentation functions. So normally, if you were to do this measurement and the corresponding calculation with just a single hadron at the time, you would convolve the transfer momentum PDF with the transfer momentum fragmentation functions. And the only thing that you would be sensitive to when doing the measurement is the convolution of the two. So the jet measurement actually allows you to break that convolution and be sensitive only to the PDF part. So in that sense, it's a more powerful tool. But in any case, it's a complementary tool to the standard semi-inclusive deep inelastic scattering, which is like the standard over many years to try to constrain TMDs. So this is a bit more detail. This is from the Liu et al. Paper. And it argues that if you measure the imbalance between the electron and the jet, then you become sensitive, as I said, to the TMDs, which are shown here. Let me just try to get your attention. So to this factor, which is a transfer momentum dependent PDF. Okay, so this is if you measure the so-called QT distribution, which is a momentum imbalance. There are two aspects that are actually quite interesting from this paper. One, that they suggest to actually measure this reaction in the laboratory frame. So defined as in this diagram that you can see here, with the beam axis as the C axis of the reaction. That might sound trivial to some of you who are used to working in hadron colliders, because that's the way we do it in hadron colliders, and there's nothing special about it. But actually, in deep inelastic scattering, that is hardly used. Almost all jet measurements, actually, in the HERA experiments, were actually done not in this frame, but in the bright frame, and that changes quite a bit, both the structure of the factorization formulas and experimental aspects related to the measurements. And so I think that is actually quite interesting and unique that this paper introduced. So not only reinvented this channel that was considered a background before, but also on top of that, it created motivation to do these measurements in the laboratory frame. So here you can see a bit more detail on the factorization formula. It involves a transverse momentum dependent PDF. It involves the hard function that is calculable in perturbation theory, and some soft function that actually is non-perturbative. So the non-perturbative component is encoded in the soft function. We'll move on. Oops. So one of the things that we did recently with my collaborators, is to use that framework that I just described to actually project, to see what we could do with those measurements at the EAC, meaning we explored how well we could do this measurement using simulations, and we explored what are the current uncertainties in, for example, the Sieverts TMD. So if you do this measurement, when you look at the electron and jet balance, and then you look for transfer, you flip the transfer polarization of the proton, you become sensitive to that PDF. And we showed that actually the measurements that we expect at the EAC will be actually very precise and very accurate. And they will allow us to constrain the Sieverts function very much. Okay, so this is an example where the particular kinematics of the event is on average about x of 0.2, which is where the Sieverts function actually is maximal, and at high Q squared. So we took that, we made those predictions, and we did later use the same channel, the lepton jet balance events, but we looked inside the jets to see what is the fragmentation pattern of the jets inside the hadrons inside the jet, and how that changes when you flip or when you change the transverse polarization of the proton. That is actually sensitive to the so-called Collins asymmetry. And so we did, again, a projection of this measurement to see how well we could actually do those measurements, what would be the detector requirements that we found in doing these simulations, and what is the theory error in different kinematics. And this is what you can see here. Each panel represents a different kinematic region, and theory bands represent the error. So the bands represent theory uncertainty, and the projected precision and accuracy of these results are shown in the error bar. So the error bar, again, for the EAC, we will actually be able to constrain this very much. And this is not a measurement that can be done in any other facility. This is really, you need the electron deep inelastic scattering and the jet. It requires a balance between them, and then try to look at this. And other more recent papers have actually explored the full potential of this channel. You can actually become sensitive to all sorts of TMD functions and evolution effects. So that is actually good, but we can do better than that. We can actually explore the feasibility of these measurements, and more importantly, to test the TMD calculations with the unpolarized data taken at HERA. So what we did in the last couple of years is do simulations for the EAC, project EAC measurements, explore that. But we can do actually similar measurements at HERA. So this is what I'm trying to illustrate here: lepton jet balance at the EAC, simulated data and real data on the right-hand side with the HERA experiment. Now they look very much the same. The beam energies are different. The HERA experiments, the HERA collider had a higher center of mass energy than the EAC, but if you control by the transfer momentum of the jets, you actually get events that look very much similar. It's just different center of mass energy would mean that you cover different kinematic regions. So you may wonder why a pathfinder program for the EAC, in particular for jet physics, future jet physics at the EAC with HERA. And there are various reasons. One is that if we do this, we will be able to keep our theorists sharp. And by that, I mean that whenever they come with some idea and then you propose observable, they will do calculations, and we can actually test that right away to see whether that makes sense in unpolarized collation. So we don't need to wait until the EAC comes to actually test those predictions. And by having a test of those predictions and an iterative process with the theorist, hopefully we will get a faster development of the TMD framework, and in particular on the jet physics aspect of the TMD framework, which is a new addition to this type of studies. Moreover, if we do this Pathfinder program, we will keep also experimentalists realistic, because one thing is to do projections and work with simulated data, but a very different thing is to actually do the measurements and do what it takes to publish a cross-section. We all know, well, those of us who have done that, that those two things are very much different. Okay, so that it keeps us realistic, so that we don't get carried away by the pretty simulations, but actually explore what are the key limitations of these measurements and what we can and cannot achieve. Moreover, when we do that exercise, that helps us to actually identify what are the key drivers of the detector performance. And that, in turn, allows us to actually have a better design or a more informed detector design, which is precisely what we are doing as we speak for the future EAC experiments. Moreover, if we have this Pathfinder program, we will be able to rethink very basic methods that were used typically in deep inelastic scattering. And if there are new ideas, we will be able to deploy those new ideas. And by that I mean basic assumptions that are related to kinematic reconstruction. So how you actually measure X and Q squared in deep inelastic scattering, which is not trivial. And there are ideas how that can actually be improved. Perhaps new jet algorithms, more dedicated to the type of events that were not studied at HERA before and demand new jet algorithms. Perhaps explore new ideas coming from the aspect of dealing with QED radiation, or machine learning, or unfolding, and the list goes on and on. All of those aspects, we can really test them and deploy them with real data, and more importantly, with real deep inelastic scattering data, which is unique in its features and rather different than the data and the collection systems in other hadron colliders. Moreover, what is interesting about the HERA data is that really has the potential to constrain phase space that is not otherwise constrained at all. So, for example, here I am showing you an event display, a figure that shows the kinematic coverage of different experiments from this paper that you can see in the bottom. And the lower right corner shows basically fixed started experiments. And the rectangle rectangular shape that you see in the top is LHC experiments, or collider experiments, actually, Tevatron experiments. And there is a gap between the fixed started experiments and the high energy collider experiments. We don't have measurements that actually aim to constrain TMD functions in those areas. And I know here I'm not being completely fair. There are some measurements, in particular at RIC, and in particular with the star detector, that should be in this plot, but they are not in this particular case. Okay, so there are, but in any way, there is potential for new deep inelastic scattering measurements, which would allow us to really merge these two areas. And because we don't have TMD measurements or measurements sensitive to TMDs in that area, that is very much unknown. We don't know really what is how these functions evolve when you change X and when you change Q squared. And there are very much there is a strong this has been studied in detail from the theory community, but until you don't have real data to compare with, I would claim that this is very much unconstrained. So this is what the potential of the HERA data has. It is to constrain the TMD evolution. And it will, moreover, it will bridge the deep inelastic scattering from fixed target experiments to the high Q-square Drell-Yang measurements at colliders. When you do that, we will be able to actually fix open issues related to TMD factorization, TMD universality, and other aspects that are unknown or not constrained regarding the TM devolution. And this is why I'm showing you here approximately what is the HERA coverage. It's a huge kinematic coverage, which in part will overlap with the EFC coverage, but the HERA data is already existing and we can actually exploit it right now. And this is what I like to call the end game for evolution. So we do have in one corner fixed target experiments, previous experiments and ongoing experiments at Jefferson Lab, Hermann's Compass experiments, which will cover a region of Q-squared between 1 and 10. And then we have the very high brilliant data from colliders at the LHC and at the Tevatron, but we have a huge gap in between. And that huge gap can be completely covered by HERA data. And once you have that, you will have 3-4 orders of magnitude in which you will be able to vary the Q-squared and check whether the calculations and the treatment of the TM devolution makes sense. Okay, so that is the motivation, and now I will start showing you the results. So this is a new result that just was published or that was submitted to the archive last at the end of August. This is our archive number, and I will describe. This is our first measurement in this pathfinder program with HERA, with H1 data. Actually, it's an H1 experiment at HERA, not in general at HERA. So I will describe to you what the H1 experiment. You may or may not have heard about the H1 experiment recently. So this is a typical general purpose collider experiment that has tracking system in the center, calorimeters, and muon systems at the outer layers. So the tracking system is composed of silicon trackers, but the technology from the, I don't know, 80s or 90s. So all silicon tracker technology, not very good, and jet chambers and proportional chambers. So that those are gas detectors. On the calorimeter, we do have H1 had a liquid argon calorimeter, both electromagnetic and hadronic sections. And in certain areas at low angles, it had a spacal calorimeter. Interestingly, the information from the trackers and the calorimeters were combined in an energy flow algorithm. Basically, you take the best measurement from either the tracking or the calorimeters and combine it in an optimal way. This is what the H1 used to do, and what, for example, CMS experiment at the LHC does now routinely. And the measurement at HERA is actually built upon many years of refinement of this detector. The H1 collaboration did a tremendous job over many years, over more than 20 years, on understanding the response of the detector, improving the performance of it. And ultimately, they achieve a 1% jet energy scale, and between 0.5 and 1% lepton jet energy scale. That is actually quite remarkable. Just to put that in context, I figured I would show you what other experiments, for example, at the LHC, have achieved. So you see here on the left, the jet energy scale uncertainty achieved by Atlas, and on the right, the one achieved by CMS. At high energies, they achieve a jet energy scale of approximately 1% or even better in some cases. But when you go to lower energy, like a 10 GeV transfer momentum or so, the jet energy scale just explodes. And there are various reasons for that. You can see the breakdown of the systematic uncertainties here. This may not be the latest and greatest version of this plot, but in general, when you go to lower energy, you become more sensitive to pileup and more sensitive to the modeling of the flavor composition of the reactions. The HERA measurement really is 1% flat all the way to 10 GeV. So it's like no match to the CMS experiments. It's much better in that way when you want to do the 1% type of measurements all the way down to 10 GeV. That can be done only at HERA. And this matters is not a small difference because the jet spectrum is very steep. So every % of uncertainty in the jet energy scale translates into a big uncertainty. Then I will mention briefly how we reconstruct the kinematics of the event. This is not just measuring the electron, it's more involved than that. It's a combination of measurement of the electron and measurement of the hadronic final state, which is by definition everything that is not the electron. And you can combine the form momentum information of those two, the electron and the hadronic final state, and you can compute the y, the inelasticity of the event, and the q squared of the event using those variables. Okay, there is a combination, a trade-off, because there are certain kinematic regions where one method is better than the other, and this particular method that I'm showing you here, it's called the E sigma method, and is particularly insensitive to QED radiation by construction. Here, I'm showing you briefly the jet performance. So this is the jet energy scale and jet energy resolution that you get with the H1 detector. And these jets were reconstructed using the energy flow algorithm. And so in the green, you see the, not green, orange, you see the jet energy resolution. Just to give you some sense, at 40 GeV, that energy resolution is 10%. And then it gets better with increasing energy. Okay, of course, what we need to do is to correct for that, correct for the fact that we have a finite resolution of the detector. What we are using for this measurement, we're actually using a brand new method that was published in this paper that you can see in here last year. And it's a method that does unfolding using machine learning. I will refer to you to the paper or Ben, who can explain this much better than myself. Who is on the audience, and but the main idea here, and this is illustrated in the paragraph, in the diagram. The main idea is that you actually reweight the Monte Carlo in a way that first matches the data, and then in an iterative procedure, you use machine learning to actually get a classifier that will ultimately give you the truth level information. So you are going to get out of the detector effects by doing this procedure, just like in a normal unfolding procedure, but this is like unbinned. Oops. Anyway, this is an unbinned type of approach. So what the first step in this approach is to reweight the Monte Carlo to match the data. And the neural networks actually are a perfect tool to do this in an unbinned way. And for example, here on the right-hand side, you see two different Monte Carlos, Django and RapGap, and they are different in general. The purple distribution is different than the green distribution, but you can use this method to reweight one into the other, and that is not very impressive, because I am only showing you one-dimensional distribution, and it's trivial to reweight one into the other. You would just take the ratio of the two distributions, and that would be it. That's how you would get the black distribution by construction. But it gets more complicated when you do this in a multidimensional fashion. As anyone who has tried this will realize that even if you have a high enough dimensionality, then this problem becomes very much difficult. But these neural networks are just great to deal with those type of problems. And this method actually allows you to do reweight the Monte Carlo so that it matches the data quite well. And this is one example of this. We can do this simultaneously for 8 different dimensions. Here I'm showing you a few distributions of the kinematic variables of DIS or the jet kinematic variables. And in general, you can do this and it works beautifully well. It even works not just in one-dimensional plots that I showed you before, but it actually works if you change one variable and then just look at the other. So for example, each panel here shows a different Q-squared range, and the variable itself is the azimuthal difference between the electron and the jet. And in each case, the black distribution matches the green distribution very well, even though the starting distribution, which is the purple, had significant differences. So this, the plots that I'm showing you are actually binned by construction, because I'm making a histogram to make this plot. but the underlying reweighting is unbinned. And that's the beauty of it. You can easily change the binning or look in many multiple dimensions, and the result will not change, or the underlying method doesn't change. And that's the first part. But of course, the second part is that the part that we have to deal with is the so-called response, the fact that what we measure is not the same as the truth level information that we generate in our Monte Carlos. Typically, what you do for normal unfolding methods is that you construct response matrices that look like this. So in one axis, the particle level, and in the other axis, the reconstructed level, and hopefully you get some sort of diagonal matrix. And basically, the process of unfolding is more or less to invert this matrix, subject to the statistical fluctuations of the data. And this is but this is not what we use for the unbinned unfolding. This is just for your reference, just to give you a sense on how well we can actually measure the jet PT and the jet absolute rapidity, and these are binned. But this is not what we actually use in the unbinned unfolding. It doesn't work like that with Omnifold. We don't need to even define a response matrix. We just use the reweighting procedure that is aided by the machine learning. And these are just different response matrices, this time for the momentum imbalance on the left-hand side and the azimuthal angle distribution on the right-hand side. Here is the left-hand side in particular is a little bit less diagonal. It has a bleeding from the diagonal to the off-diagonal terms, a bit less so in the azimuthal distribution, which is on the right. That tells you right away that actually we can measure better the angle, but it is a bit more difficult to measure the momentum imbalance, which is on the left-hand side. But we do both, and there are arguments which actual observable we should report, but we don't pick just one. We report both actually at the same time. So in general, this is the procedure. There is as I described to you, the first part, which is the reweighting of the Monte Carlo to the real data, that works beautifully well. And then the second part is reweighting to the generator level to basically unfold the distribution and get back the truth level information. I will refer to you for more details on this nice paper if you want more details, but I will show you now the results. The first thing that we do, and this is something we would do for any type of unfolding method, is to do closure tests. That means that we do construct a pseudo data set, and then we apply the machinery on that pseudo data set. In this case, we have two independent Monte Carlos. One is Django Monte Carlo generator, and the second is RapGap Monte Carlo generator. We treat in particular the Django as a pseudo data, and then we use the RapGap to do the unfolding within this method of Omnifold. Here, what we want to compare is the result, like the unfolded distribution, when you use the pseudo data compared to the truth value. Because we know this is a pseudo data, we know what the truth value is, so we can compare what we get out of this black box and what we put in. And by comparing that, you can actually gauge systematic uncertainties. And you can see here the dotted lines represent the truth value, the markers represent the reconstructed value, like the unfolded value, and it is very much on top of the truth value. And the ratio shows you that there is a small relative difference that actually is accounted for in our systematic uncertainties. There are various ways we do that. We either use Django for the unfolding, or we use RapGap. We also did unfold one onto the other and vice versa. We did various tests, and the systematic uncertainty that we get at the end is at the percent level for both the transient momentum dependent cross-section on the left and the pseudo rapidity, which is on the right. And similarly here, I'm showing you the QT distribution, which is the momentum jet imbalance, normalized by the Q of the event. And on the right-hand side, I'm showing you the azimuthal angle difference. In both cases, the closure test works remarkably well. The maximum differences that we observe between truth level information and what we get out is at the 10% level. And that is the maximum systematic uncertainty that we report in the extreme areas of phase space. by and large, the systematic uncertainty is constrained to the few percent level. There are also some corrections that we apply, and which are the hadronization corrections. These corrections are applied to the perturbative calculation. They are not applied directly to the data, which is different from what H1 experiments and HERA experiments in general used to do. This hadronization correction is taken from Pythia, basically, and with hadronization turned on or off. And we actually obtained also from Herwig, and we apply this as a multiplicative factor on the next to leading order calculation, which are at the partner level. So this correction translates the partner level calculation to a Hadron level calculation that we can compare to the data. These corrections are actually very small, and they are, as you can see from the plot, very less than 5% for most of the kinematic range in the PT spectrum on the left, a bit larger on the QT spectrum on the right, and they are actually very similar between Pythia and Herwig. That tells you that actually this is actually very well constrained, even though the underlying models that Pythia and Herwig use are very much different. And so we apply this correction to the NNLO calculation, and we take the difference as a systematic uncertainty on that prediction. Here I'm showing you the systematic uncertainties of our measurement. The black dotted line represents the total uncertainty, and on the left-hand side, I show you the total uncertainty for the transfer momentum, and on the right-hand side, I'm showing you the pseudo rapidity. And the breakdown of the different systematic sources are shown in here for different colors. They involve the measurement, how well we measure the scale, the energy scale that affects the hadronic final state measurement, how well we measure the azimuthal angle of the hadronic final state, how well we measure the electron energy, how well we measure the azimuthal angle of the electron, and they're related to the unfolding process. How that unfolding depends on the underlying model that we do need to put in the Monte Carlo. By and large, the systematic uncertainty is at the level of a few percent. The total systematic uncertainty ranges from a few percent, a couple of percent, to 10% in total. But each one of the sources actually is fluctuating at the few percent level. To be honest with you, we had very much difficulty to actually computing these uncertainties simply because they were so small. They are actually hard to constrain. This might be even an overestimate or what the true uncertainty is. So we are going conservative in this measurement. But by and large, you see the systematic uncertainty very small. So this is a precision measurement. And this is in part because the H1 measurement, H1 experiment is actually very well calibrated. Here, this is the same systematic uncertainty plot, but now it is showing you the systematic uncertainty for the QT distribution on the left and for the azimuthal angle distribution on the right. The azimuthal distribution, the momentum jet imbalance on the left, has some systematic uncertainty that reaches up to 15% in the maximum, at maximum, and that's the extreme kinematics, and that's dominated by the model dependence of the unfolding process, but by and large is about 5% or less for the entire phase space. Similarly, for the azimuthal angle, the total uncertainty ranges from about a couple of percent to 5% or a bit more over the entire range. And what's interesting is that we are, as I told you before, we are actually able to measure the azimuthal angle much more accurately and precisely than the elliptic jet imbalance. And that was reflected in the uncertainties that we assign for these measurements. The azimuthal angle uncertainty is just 4%, 5%. So these are the results. This is the jet transfer momentum, okay, for the kinematic region that you can see in here, Q squared above 150, the Y region between 0.2 and 0.7, and the minimum transfer momentum of the jet 10 GeV. We use the anti-KT algorithm and radius 1.0. And you see here the data is shown in the black markers. The different predictions from Monte Carlo generators and analytical calculations are shown in different colors or bands. It's hard to see from the plot above how well they compare, but if you look at more closely at the ratio, you see first that data is actually very, very accurate and can constrain the difference between the models very well, and is actually very well described by the next to leading order calculation, which is shown here in red. A variety of Monte Carlos also are able to describe this. And especially Herwig and Django. The time. Sorry, with this. Okay, so the next result that I'm going to present is the jet fluid rapidity. So this is the jet fluid rapidity for minimum jet momentum, transfer momentum of 10 GeV. Keep that in mind. This is a measurement that was on purpose done at the lowest momentum that we can reach, yet have an accurate measurement. So it's 10 GeV, a radius of 1.0. See here, the fluid rapidity distribution is very well described by some Monte Carlos, but the analytical calculation, in particular the next to leading order calculation, fails to describe the data, and particularly at large fluid rapidities. That is actually expected. This process, and in particular this observable, is very sensitive to higher order terms. So next to leading order calculation would do a better job. And when that becomes available, we will make a comparison. But those two things, the jet fluid rapidity and the jet transfer momentum, are not really the main purpose of the measurement. Those were a baseline measurement that allows us to constrain the analytical calculations, the PQCD calculations, collinear calculations, to constrain them so that we later can do this measurement, which is the main point of the measurement, which is the lepton-jet imbalance. As I described before, the lepton-jet imbalance is defined as a momentum imbalance between the lepton and the jet. That's QT, normalized by the value of Q of the event. And this is how it looks like. It's a bit busy, the plot. We had to condense lots of curves to fit PRL limits. But let me just guide you through this. The data is actually very well described by a bunch of Monte Carlo generators, and is well described by the PQCD calculation at high values of Q. You see the red curve here is actually quite well described by the red dots. At low values, the red dots or red bars lines actually diverge, and that's an expected behavior. And so they were not able to actually constrain, they are not able to describe the data. Whereas the TMD calculation, which is shown here in the blue line, is able to describe the data at low values of Q, and also to medium to high values of Q as well, but it fails to the highest values that we can reach. So what is important to realize is that that calculation actually describes the data quite nicely, and moreover, there is a big area of overlap between the collinear calculation and the TMD calculation. Also, the Monte Carlo generators do quite a nice job describing the data. In particular, also these two Monte Carlo generators who are using TMD physics inside the Monte Carlo generators. And here you see the more traditional Monte Carlo generators like Pythia and Herwig and Django and Radgat also doing some reasonable job in some limited areas. So that is our momentum imbalance. Here I'm showing you the azimuthal correlation, very similar picture. TMD calculation does a great job at low values of the azimuthal angle. At large values, it fails, and vice versa with the PQCD calculation. Okay, and as you can see here, the data is even more precise in the azimuthal angle measurement than in the momentum imbalance measurement. So those are the results, and let me just tell you that Omnifold, this new method, machine learning based method, it allowed us to do this measurement simultaneously in all these observables, and actually in 8 dimensions. We report 4 variables, but we did the unfolding in 8 dimensions and in an unbinned way. And this is the first measurement that actually uses machine learning to correct for detected effects. And it will not be the last one. Yes, this is a really nice method, a very powerful method, as I will show you in a second. Yeah, so in particular, what we report as a cross-section measurement, what we send to the journal, is really a binned measurement. So after we got our unbinned results, we computed bins and we made histograms, and then that's what we put in the journal. But in fact, what we got back from the methodology, is actually an unbinned result. And this is evident, for example, when you go and want to compute the correlation matrix. So this is actually very powerful because it allows us to see what is the correlation between observables. Here I'm showing you the correlation coefficient for different bins and different observables. All of this was simultaneously unfolded. So we got this for free, this type of matrices, the high dimensional matrices, to compute the correlation terms between observables. And it's been here for reference. Obviously, to make some histogram, we would need to actually make a bin, a version of this. But in reality, we have the information unbinned. And here, what is interesting is that there is a very strong correlation between the QT measurement and the azimuthal angle measurement, which is expected. But here we can actually quantify how overlapping those two measurements are. How correlated they are. So the bottom line that I want you to get across from this measurement is that the TMD calculation that we showed, which by the way was completed by Feng Yang, and we also had calculations by Yongbo Kang, has no free parameters and describes the data over a very wide kinematic range, actually beyond what is typically considered the limit of the applicability of the TMD framework. So roughly Q squared divided by QT divided by Q of about 0.2. If you can see here, the blue distribution describes the data well beyond that. So actually that's very interesting. It also tells you that the TMD calculation that used as ingredients the soft functions and the TMD PDFs that were extracted from low energy, low Q squared DIS data and RealYAM data actually describe this high Q squared deep inelastic scattering data without any problem. I think that is what non-trivial to foresee or to predict. We didn't have evidence that would work, but it actually works to a remarkable degree, and even works to very low Q squared, very low PT of the jet. So as I told you before, we did this on purpose to construct this measurement in a way that we are going to prove the first step, the lowest jet that we could do, which is 10 GeV in the case of H1, and still get a very accurate result. There is another aspect of this which I want to get across, is that we observe for the first time in deep inelastic scattering that the calculation in the TMD framework matches a calculation in the collinear framework. That is highly non-trivial. There is a big overlap area at mid QT, in which both calculations are on top of each other, and both calculations describe the data. Then you see at both extremes, one of them fails. In the lower QT extreme, the PQCD calculation fails. In the high QT extreme, the TMD calculation fails. And so that tells you that actually you can force these two frameworks to merge into one another. I think that's very interesting. Now, in the final minutes of my presentation, I will describe what will come from the future of this Pathfinder program, briefly. First, something we have at hand is to look at the Q and X dependence of the momentum imbalance that I just showed you. We have that, as I showed you, we did an unbinned measurement. So it's actually rather straightforward to generalize our first paper, followed that up with an extensive paper that will chart the kinematic gradient that I am showing you here. Above the red line, that's going to be our first measurement. Later on, we can actually expand that to lower values. The minimum Q-square that we can reach, HERA measurements used to report jet measurements, is about 5 GeV. So that will also come. So as I said before, the end game is really to look into the complete Q-squared coverage and constrain this TMD physics in the unpolarized section. Let me just tell you that one thing that we will definitely do in the near future is to constrain a new observable that was proposed very recently by Feng Yuan and collaborators in these 2 papers, in which they look into the impact of the soft gluon radiation in the dijet and lepton jet production at different colliders and different systems. And they have predictions. So this prediction that I'm showing you here is for EIC, that stipulates that if you look at the azimuthal angle between the 2 jets, that is actually that distribution of that angle is not uniform. It has a cosine modulation, and which is in the case of lepton jet production mostly a cosine phi modulation, but depending on the QT, you will get different moments. And so this is coming from just soft gluon radiation, but it's a very important baseline for future measurements that will try to constrain primordial modulations. What we mean by primordial is modulations that are coming from gluon TMDs and Wigner distributions. So this is predicted to be like a foreground or background for those type of studies. So Feng and company predict a very large, as you can see from this plot, they predict a very large cosine modulation. Because the higher moments that you see in the dotted lines are very small, low Q. Actually, that's precisely what we see. I mean, this is an internal plot. We need to do the measurement, but actually, this is almost a byproduct of our previous measurement. Because the previous measurement was unbinned, we can recompute with the unbinned result. We can recompute this new observable that we didn't have in consideration when we started the measurement. And so this is a beautiful example of the power of unbinned measurements. And you should expect results quite soon. So this is something that in particular, Ben Nachman and his group is looking into. You see here a very recent discussion we had actually. And the data is very beautiful. And it provides these nice cosine distributions and with higher moments and so on. And we will see more results quite soon. We already have the results at hand, given that our first measurement was unbinned. So let me quote from the Omnifold paper that says that the Omnifold, the way that this method allows you to do unbinned results, to get unbinned results, means that you will be able to perform a measurement even for future, that is going to be future proof, in the sense that you will be able to recompute observables that were not yet invented at the time of the analysis. So this is a quote from the paper, and let me tell you that is true. And that's precisely what we did. Feng's paper was not invented. So these studies are actually also true possible in the bright frame, in complete analogy to deep inelastic scattering, but they require dedicated jet algorithms like Centaura, and that's another thing that we will be able to do. And this is something I'm working on right now as we speak. There might be a very large overlap between what we already published and this type of results, which works in the bright frame. This is something that we want to explore. How much the same, or what is the overlap between the lab frame results and the laboratory frame result? And that's something we will be able to do with a different jet algorithm. The other thing that we want to do is to do gluon TMDs, and the prime way to do TMDs is with gluons. Once you do gluons in the HERA collider, then in this type of events, in deep inelastic scattering, you're directly sensitive to the gluons when you have 2 jets in the final state, 2 high energy jets, high PT jets in particular, recoiling against each other in the bright frame. So this is actually one of the promising ways that we have people anticipate to do measurements at the EAC with this type of events, where you see digits. And this is actually the most promising way to go and constrain the gluon series function. As you can see in here, some predictions, some projections for the on the gluon series function on the right-hand side, and some event display on the left. We can actually do these measurements. There are plenty of digit events at the EIC, sorry, the HERA, and at HERA we will be able to constrain the unpolarized gluon TMD sector. And so this has been done. Digit measurements have been done at HERA. The only new thing that we will be able to do, that we will do, looking forward for the EAC, is to measure the azimuthal angle of these jets, which hasn't been measured. That will allow us to constrain gluon TMDs. Moreover, we will be able to explore diffractive digits, which is something that recently has been proposed as a way to explore the Wigner distribution, which was, as a few years ago was not known that you could do that. And this is the holy grail of 3D imaging studies. And you could, in principle, do this measurement if you were able to constrain two jets, diffractive digits, and tag the forward proton in diffractive interactions. So this is how a simulated event of that type would look like. And basically, you want to measure the azimuthal angle distribution. This measurement has been done at HERA. There is a beautiful measurement instrument that is called the forward proton spectrometer. And I'm showing here what the instrument looks like, what is the kinematic coverage of that instrument, and the measurements that were done. So the measurements inclusive diffractive interactions on the left, the digit pseudo-repeated difference on the right. So this measurement is actually very keen. The drawback or the limitation is that the statistical uncertainty was actually quite large. But a first look into this channel might be possible. Just in the same way that the azimuthal difference between the jets was reported, we can just report the azimuthal angle difference. And that data is in there, and we should be able to reanalyze that. I will skip this, but just tell you that, of course, what we plan to do is to do jet substructure, which encodes quite rich dynamics, in particular TMD dynamics. One of the measurements we plan to do is hadron jet measurements, which are a generalization of cities and will allow us to constrain unpolarized fragmentation functions. So in summary, the HERA data is a treasure trove that will keep us busy for the 2020s. We are just starting to analyze the data, but this data has tremendous potential and to boost EAC science during the 2020s. So I would invite you to mark our calendars to discuss these exciting possibilities next May or June, where we are going to have a workshop dedicated to this, to see how we can actually use the HERA data to constrain the physics and develop the physics of the EAC. So in summary, I presented you a new measurement of lepton jet momentum and azimuthal imbalance in DIS, which provide a new way to constrain the TMD PDFs and their evolution. We have that the TMD, we have seen that the pure TMD calculation does a great job at low Q, fails at high Q as expected, and vice versa for the collinear PQCD calculation. There is a big overlap between the two calculations at mid Q. And this is the first measurement ever that uses machine learning to correct for detector effects. And this is the first measurement in a series of studies that we will do in order that aim to create a pathfinder program for the EIC. So thank you very much, and sorry for being a bit over time.
Well, thank you very much for such an exciting talk. I'm sure there's questions. I think the first one is Fan.
Miguel, very nice talk. Thank you, and also congratulations to you and Ben and the others to pull this out. I think it's very, very nice, very beautiful result. Oh, I have a couple questions, and maybe I just ask and then you just reply if you can. So first question, I think this unfolding method is very powerful. So has this been applied to, or maybe in the future will apply to HC kind of measurement?
Yes, as far as I understand, Ben is working on a Atlas measurement, and I expect that other measurements are ongoing in other experiments as well.
Okay.
Maybe Ben can comment on that.
Okay, that's very good.
Yeah, I don't have anything more to say, unfortunately, but yeah, it's in progress.
Okay, yeah. That's good. That's good. Another quick question. So on your slide 36, you don't have to go back. You have this uncertainty coming from for the QT over Q distribution. The dominant contribution coming from so-called model. I actually don't know what the model means.
Yes, that's a good question. So here, this is to illustrate this fact. So when we do the unfolding, we need a Monte Carlo generator, and in principle, we try our best to minimize the dependence of the results on the choice of that particular model, but there are differences. If you use either RAPGAP or Django, you will get a slightly different result. And that at the extreme kinematics, in particular the low Q, that is up to 10% relative difference between the results. And that is where that uncertainty is coming from. Ultimately, is the choice of Monte Carlo generator that you use to correct the data. So that is where this is coming from, and that's a limiting factor that we have. In a sense, that is the limiting factor.
So can this be improved in the future? I mean, you mentioned this really depends on the Monte Carlo generator, right? So I don't know. This just also tells you that actually in this Monte Carlo generator, they may have different approach to generate finite transfer the momenta in the potential, right?
Yes, there are slightly different. Kinematic distributions. We did reweight each one of them independently to data, so that reduces greatly the dependence that we have on the underlying distributions. But that doesn't reduce it to the 0% level. In this particular case, the maximum we got is 10%. We need to find out, and we need to see what is the level of uncertainty that we will get at different Q-squared ranges. It might be lower.
Okay.
But at this particular kinematics, which is shown here, Q-squared of 150 and PT greater than 10, that's what it is. I don't see a way that we would be able to reduce that. For different kinematics, it might be better. I suspect that it will be better, actually. Does that answer the question?
Yeah. Thank you. Xuenian, that's it.
Thank you.
Okay. Any other question? My simple question. Okay. Let me see. Let me ask my first. Then there is another question from Farid. This kind of machine learning unfolding method is it possible to to apply to heavy ion like jet analysis?
Yes, I think so. Yes. Yeah. So this is very, very general. It doesn't depend on the underlying physics. It's a general method to correct for detector effects. So it would work even in experiments that are not as colliders, in principle. Just as a general thing that every experiment needs to do is to account for the detector resolution.
Of course, in heavy ions, the sort of background is sort of large, huge. The background subtraction is an issue.
That is a good question. That's a good thing, a good point. Yeah. So as you said, the heavy ion environment is more complex. You not only are fighting with detector effects, which is all that we are dealing with in the DIS, but on top of that, you're dealing with a background that is fluctuating in a way that might not be that introduces biases. So it's a different problem fundamentally. It's not just detector, but it's this background that you need to subtract.
Mm.
So it might help to have an unbinned result, and especially a way that you can reweight the Monte Carlo so that it matches the data. That might help. I'm sure people are looking into this, and you will know. Well, I'm not sure. I strongly suspect that people are looking into this and applying it also for heavy ion data.
I see. I see. Okay, Farid, go ahead.
Yes. Hi, Miguel. Very nice talk. I have a peripheral question on one of the slides on the semi-inclusive digits that you mentioned. So how could we be sure that we are probing the gluon TMD and say not the quark TMD? Like, how can you distinguish which channel is being probed? Do we have control over whether the jets are initiated by quarks versus initiated by gluon?
That's a good question. Yeah, we don't do any sort of tagging for this measurement. We just take any event that has a jet that balances with the electron, but we're inclusive. So in the sense, we also have topologies that have more than one jet, and the lepton and the leading jet are not back to back, but there is a big angle between them. So those multi-jet events also show up in the distributions that I just showed you. So obviously here, where are this? Sorry about this. Takes forever. So for example, here, the large delta phi are caused by events that have multiple jets, and those will be initiated by like gluons. So in a sense, yes, this is not just pure quarks, but the expectation we have is that when you go to low values of Q, that very much suppresses these multi-jet events, and the distribution should be dominated by the quark TMDs. But that's just my naive interpretation of the calculations. I don't really know to which degree this is dominated by quarks or dominated by gluons, and to which degree that varies with Q. I cannot give you a quantitative answer other than qualitatively say that we expect that the leading order diagram is coming from the quarks and is dominant. But in different phase space, in different regions of the phase space, we will have a different breakdown of the different channels.
I see. Thank you, Miguel. And I guess the opposite game is played when one is studying the dijet process. So I think you had it on one of your slides later during the talk.
Yeah, this is actually very common. This channel was studied at length at HERA, and much more than the single jet. And indeed, the idea is that you are more sensitive to gluons, but of course, this is not the only diagram that contributes to this. And there are other diagrams that actually are quark initiated, and they're not directly sensitive to the gluon TMDs. So in that case, you would need to do the proper calculation and account for the different channels, and from that, try to disentangle that and get on the gluons. And that is something that I guess that is actually needed from the theory. From the experiment, we may actually be able to tag the jets by doing some simple quark or gluon tagging. In principle, that would, for example, in here, if we were able to tag the two jets as quark jets, then that would enhance the gluon sensitivity. That is something we might try. But that is also, we will do the inclusive measurement, which you just measure every digit.
Right.
Yeah.
Thank you.
Thank you.
Okay, I think if there's no further questions, and we thank Miguel again for this great talk.
Thank you very much.
Congratulations again.
No, thank you.
Thank you, Migue.
Mm.
And see you soon.
See you. Bye-bye.
See you. Bye.